Hello, so good morning. Okay, so first of all, sorry for this little bit of delay for the second upload. Anyway, so here are the solutions for INMO 2019. So this exam was held, as you know, it was 1 month back, a little bit more than that. Anyways, so there are uh, yeah, 6 problems and 4 hours to solve it. So yeah, let's go. So this is problem one. It says ABC is a triangle with angle BAC greater than 90 degree. Okay, like this. Let D be a point on the segment BC and E be a point on the segment AD, such that AB is tangent to the circumcircle of triangle ACD and BE is perpendicular to AD. So like this is here. This is the circumcircle of ACD. AB is a tangent to the circle, and okay, and it's given that A and BE is okay. ACD at A and BE is perpendicular to AD. So this angle is 90. It says CA equal to CD. So these two blue lines, they are equal, and it says AE equals CE. So these two red lines are equal. It says determine angle BCA in degrees. So this is the angle alpha that you have to find in degrees. Alright, so how do we do this? So let's say these two angles are theta. So then since this is isosceles, so these two angles will be equal, and this angle here will be equal to also theta. And next is I just label the sides. Let's say this is B, then this is also B. Let's say this is C. Let's say this whole length BC is A, then BD will be A minus B. And since we know the angles, so this length AB will be 2B cosine of theta, right? So because if you drop a perpendicular from C to AD, this half length will be B cosine of theta. So the whole length will be 2B cos theta. And this we know is A minus B. This angle is theta here, so this is A minus B cos theta, and this angle, this side here is A minus B sin theta. Alright, so what else? So we have this length AE is equal to this length CE. So we can write AC in terms of the side AE and the lateral angle theta. So AC will be this length AE, which is A minus B cos theta, and 2B cos theta, that will be A plus B cos theta, into the cosine of the lateral angle, that is theta. So B equals 2 into A plus B cos theta into cos theta. Okay, so that's how it is. And after that we have sum of these three angles is 180. So 2 theta will be 180 minus alpha. So cos 2 theta is minus cos alpha. So this we can convert it to half angle. Cos square theta is 2 cos square theta is 1 plus cos 2 theta. Then that is 1 minus cos alpha. And from there we get basically cos alpha is this, A by A plus B. So next relation that we have is this length, AC square, AB square is equal to BD into BC, and AB square also equals BE square plus AE square. That's right. So square of this length plus square of this length is equal to BD into BC. So that's A minus B into A. You have that. So that's what we have. I just simplify it. I got cos 2 theta. Again, you can write it in terms of cos alpha here. Sometimes A square will go away, some factor of B will go out, and basically you get 2A cos alpha is A plus B, and A plus B I can again write as A over cos alpha. So that's what. And from here we get cos square alpha is half. And since this angle here is obtuse, so this angle has to be acute. So alpha is less than 90 degrees. And that basically means alpha has to be 45 degrees. Okay, so that was problem one. This is next problem. It says let A1, B1, C1, D1, E1 be a regular pentagon. And it says for 2 to 11, you take the midpoints of those pentagons and find and make another pentagon. Okay, and you keep on doing it till you basically get 11 pentagons here. So, and then it says that all the 5 vertices of these 11 pentagons are arbitrarily colored red or blue. Then it says prove that there are 4 points among those 55 points which have same color, and those points are cyclic. So alright, so first of all, what I noticed was that n equal to 11 is basically just too many pentagons. Even if you have 3 pentagons with this relation, the result will still hold. So first I had proved this result for n equal to 11 using the Pigeon principle, and that time it seemed to me that n equal to 11 is necessary and it's also sufficient. And then I thought that probably there is a counterexample with n equal to 10, and when I tried to evaluate it, basically what I found that there are a bit too many more cyclic points than you can get rid of. So eventually when I started looking down, then I finally realized that even with 3 pentagons you will get cyclic points. Okay, so I'll just show you the proof for n equal to 3 here. So first of all, let's assume that no 4 points on the pentagon have same color, because otherwise what happens is that so there's a 4 points same color. Obviously it lies on a circle because the pentagon is regular. So if you take all the midpoints, and they will also be regular pentagons. So okay, so we also only have, so now we only have to consider the case where those 3 pentagons, they have 2 points of one color and 3 points of another color. Okay, so each of these 3 pentagons have 3 red and 2 blue, or 2 red and 3 blue vertices. And since there are these 2 combinations possible, and then there are 3 of these pentagons, and you associate these 2 with 3 of them, so there is one which will go to 2. Okay, so there are 2 pentagons which basically have the same color majority. Okay, so let's assume that those colors are red. So we have 2 pentagons with the red majority here, and now we have to look at 2 cases. Those pentagons can be aligned, can have same orientation, or it can have opposite orientation. So we have to look at those 2 cases. So alright, so the case 1 is P1 and P3, they have red vertices, which basically means the pentagons have same orientation. So this is how it looks like. And so how do we start here? So since there are 3 red points on 5 of these vertex, so there will be 2 red points which will be sitting next to each other. Okay, so we'll start with there. So let's say that these 2 are red. Okay, and now how do we move forward? So let's look at this line here and this line here, these parallel lines. So what do you notice is that if on these 2 parallel lines, if let's say both are red here or both are red here, it will form a cyclic quadrilateral with these 2 points. So you cannot have 2 red points on these lines here. So you can have at most one on this, one on this, and since there are 3 red points on this one, so this point has to be red. So this is forced. Okay, and now we are basically we have a choice of how to choose the 2 red points on this. So notice that there is basically a symmetry about this horizontal axis. So you can have 2 cases. One is the case when both the red points are on one side of the axis, either these 2 red or these 2 red, or you can have one point on either side. So you have this red and this red, or this red and this red. And due to the symmetry, let's say whether I choose these 2 red here or these 2 red here, these cross points, they will be equivalent. Okay, so basically now I just have to look at 2 cases. So in case 1, let's say I choose these 2 red or these 2 red, whichever. So let's take this red and this red. Okay, because if I take this red and this red, it will be, you understand, it will be same as this. So here we had so now these 2 points will be blue here. Okay, and this side, okay, so let's sorry for that. So here we can choose the 2 points on the same side. Okay, so I can take these 2 red or these two red. And because of symmetry, it doesn't matter whether these two are red or these two are red. So let's take these two red. Okay, so we have basically two configurations that we have to look at. So in this case, here these two will be blue, and these two will be blue here. And now what you notice is that in this one, these two are red here. So if these two are red, it will be cyclic with these 4 points will be cyclic. So this point has to be blue. Similarly, this point has to be blue. Otherwise, if this is red, then these 4 points here will be cyclic. Okay, so these two are blue. That means this point is forced to be red here because we have 3 red points. And now on this one, again, it's red on this azimuth here. So you cannot have a red point here. Otherwise, this will be cyclic. And you cannot have a red point here. Otherwise, this two and this two, they will be cyclic. So this 2 point has to be blue, and since there are 3 red points here, so this is red. So, okay, so all this arrangement was forced. The only choice that we had was the choice of symmetry, which is basically equivalent of having no choice. So, but what happens here now? You see, so in this configuration, you have these 4 cyclic, and you also have this 4 cyclic, and in this one, you have this 4 point cyclic, and there is one more, which is this 4 point cyclic. Okay, so this was the case one when the 2 pentagons had the same orientation. So it's very what we have shown is that it's impossible to avoid cyclic points here. So now it's the case 2. Yeah, okay, so in case 1 we have shown that non-cyclic arrangement is not possible. So now we look at case 2 when we have P1 and P2 or P2 and P3. Basically what this means is that the 2 pentagons have opposite orientations, and when they have the same common majority, what happens then? So it will look like this. Either this will be P1 and this will be P2, or this is P2, this is P3. Again, it doesn't matter. So again, we start with 3 red points on the outer one, so that there are 2 red points sitting next to each other. So we start with this, and now you look at these points here, and basically same argument. You cannot have both of these red and both of these red, so you can have at most 1 red here, 1 red here, and since we have to have 3 red points on this pentagon, so this third point is forced to be red. So now we again have a choice of symmetry. Basically, we can choose the 2 points on the same side or on the opposite side of this horizontal axis. So again, I choose these 2 or these 2. It doesn't matter. Or in the case when I have 2 points on the same side, either I choose this 2 and this 2, or this 2 and this 2. It doesn't matter. So let's take these 2 red, and on this side let's take this 2 red. So these 2 points will be blue here, and here these 2 points will be blue. So now what? Okay, so now you look at the lines parallel to these 2 red points here. So this one and this one. This one cannot be red, otherwise this will be cyclic. Again, this cannot be red because then this will be cyclic. So these 2 are blue, and now this last point, this is forced to be red. Okay, so now in this case, let's look at lines which are parallel to this. So this one and this one. So here it cannot be red, otherwise this 4 will be cyclic, and this also cannot be red because otherwise it will be cyclic with this arrangement here. So these 2 points are blue, and this is red. So now in this case, what happens? We have this cyclic, and we also have this cyclic. And in this case, what happens? We have this one cyclic. Okay, so can you find another cyclic arrangement here? Anyways, so basically, again in this case, all the points were forced. The only choice that we had was the choice of symmetry, which is basically equivalent of having no choice at all. So what we have basically shown is that even in this case, cyclic, a non-cyclic arrangement is not possible. You cannot get rid of cyclicity here. So I've shown that, and then now it's basically we have proved that non-cyclic arrangement does not hold for 3 pentagons. And since it doesn't hold for 3, it will not hold for any higher number. So this is problem 3. Okay, so it says M and N are distinct positive integers. Prove that GCD of Mn plus GCD of m plus 1 n plus 1 plus GCD of m plus 2 n plus 2 is less than or equal to twice of the absolute value of m minus n plus 1. It says further determine when the equality holds. So, okay, since this expression is symmetric in M and N, so we can assume without loss of generality that m is greater than or equal to n. Okay, so then this expression basically becomes GCD of Mn plus GCD m plus 1 n plus 1 and GCD m plus 2 n plus 2. What is GCD of Mn? It will be same as GCD of m minus n and n. And why is that? Because the GCD will divide any linear combination of these two numbers. GCD of that, and GCD of this will divide a linear combination of these two numbers. So basically, yeah, so from there you can get this, and from there you can get this. So the GCD has to be same. Okay, same thing here. So GCD of this and this is equal to the GCD of the difference, and again the same one. M plus 2 n plus 2 will be same as GCD of n plus 2 minus n plus 2, the same minus n and 2. So that's what we get. And now how do we proceed? So let's say this is D0, let's say this one is D1, let's say this one is D2. Okay. So now what can you say about these numbers D0, D1 and D2? First of all three of them divide m minus n. Okay. And then it's what you have is D0 divides n, D1 divides n plus 1 and D2 divides n plus 2. So what more can you infer from this? So since D0 divides n and D1 divides n plus 1, so D0 and D1 are co-prime. So basically GCD of D0 and D1 is 1. And since D1 divides n plus 1 and D2 divides n plus 2, so these two numbers are also co-prime. It will, so GCD will also divide the difference. So it will divide 1. So same GCD of D1 and D2 is 1. And what can you say about the GCD of D0 and D2? So the difference of n plus 2 and n is 2. So the GCD of D0 and D2 will divide 2. So that means the GCD of D0 and D2 can be 1 or 2. Okay. So this is what we have. And now basically, yeah, it's some algebra. What works is from this set D0, D1, D2, you basically choose x0, take x0 to be the maximal value of these three D1, D1, D2, and take x1 to be the one which is co-prime with x0. Okay, so such x1 always exists, because if x0 is D0 or if x0 is D2, you can choose x1 to be D1, and yeah, if x0 is D1, then you can choose x2 to be, or x1 to be D0 and or D2. Okay, and you choose x, you have chosen x0, x1, and let's take the x2 to be the remaining third number. Okay, and why do we need this? You'll see it now. So let's look at the right hand side. It was 2 modulus of m minus n plus 1, and since we have assumed that m is greater than or equal to n, so that will be 2 into m minus n plus 1. So now this, how can you write it? Since all these three divide m minus n, so x0 is the one from the set, so you can write it as twice of x0 f0 plus 1. And since x1 also divides m minus n, and x1 is co-prime with x0, so x1 divides f0, so you can write f0 as f1 x1, and this is greater than or equal to twice x0 x1 plus 1, because f will be greater than or equal to 1. Alright, just okay. Alright, now one. So now this I basically divide it. I take x0 x1 together, and you take this one together. This I can write greater than or equal to x0 plus x1 plus x2. Why is that? Because since x1 is greater than or equal to 1, so first expression is greater than or equal to x0, and this one is greater than or equal to x1 plus x2. And why is that? Let's see. So x0 is greater than x2. So x0 minus 1 is greater than x2 minus 1. And since x1 is greater than or equal to 1, so this expression still holds. So basically you multiply it and you take x1 to the other side, 1 to this side, and you get x1 x0 plus 1 is greater than x1 plus x2. So that's what you have here. And what was this equal to? This is equal to d0 on top plus d1 plus d2. These are the same terms rearranged, and this is equal to the left hand side. Okay, so we have shown that right hand side is greater than or equal to left hand side. Alright, so now there's part 2, which says when does the equality holds. So for equality, we have to make everything equal here. So first of all, f1 has to be 1, and we also have 1, x1 has to be 1, and we also have to have equality here. So it says x1 is 1, so x0 basically has to be equal to x2. Okay, so basically that's what we have. x0 will be x2 and x1 will be 1. So now you can decide which x0 is which x is which d. Okay, since x1 is 1, so x1 has to be d1 because it will be gc, it will have it will be co-prime with both d0 and d1. So since x1 is 1, it will be co-prime with both x0 x2, so x1 will be equal to d1. Similarly, so now okay, so now you can choose, since x0 is equal to x2, so you can choose d0 to be x0 and d2 to be x2. Okay, and what you can, okay, and you also have f1 to be 1, so that means m minus n is equal to x0 into x1, and since x1 is 1, so m minus 1 is x0. Okay, and you have this. Okay, I just already explained it. The GCD of these two will be 1, so you can choose this combination. You can choose x0 to d0, x1 d1, x2 d2, or the other way around. You can choose x0 to be d2, x2 to be d0. Anyways, and we also have GCD of x0, x2 to be can be 1 or 2. So what values can x0 and x2 take? It can either be equal to, both equal to 1 or both equal to 2. Okay, so x0, x2 can be 1 or 2. So that means the triple x0, x1, x2 will be either 1, 1, 1 or 2, 1, 2. Okay, because x0 is 1, so when x0, x2 is both 1, it will be 1, 1, 1. If x0, x2 are both 2, then it will be 2, 2, 1, 2. So basically we have to just look at these two cases. Okay. Okay, so now m minus n is d0. Okay, so yeah, where was that? M minus n is x0 and x0 is d0. M minus n is d0 and d0 divides n, d1 divides n plus 1, d2 divides n plus 2. That's what we have. And this d0, d1, d2 is either 1, 1, 1 or 2, 1, 2. So if it's 1, 1, 1, what does it mean? So 1 divides n, 1 divides n plus 1, 1 divides n plus 2. All this is okay. It also means m minus n equals 1. So that basically means m and n are consecutive integers. That's what. And if d0, d1, d2 equals 2, 1, 2, then m minus n is 2. And we also have 2 should divide n. So basically means that means n is even. So and since m minus n is 2, so m and n will be consecutive events. So these are two cases when equality holds. The other things you can see it works out. So d1 is 1, so this relation is okay, and d2 is 2. So since n is even, so n plus 2 is also even, so d2 will divide that. That's okay. So for equality, we should have mn should be consecutive, or there should be consecutive events. Okay, so that was problem 3. This is problem 4. It says, all right, so basically it says there is you take n and you take a number n which is greater than n to the n minus 1. Okay, and you take basically n consecutive integers, m plus 1, m plus 2 till m plus n, all greater than this number. So very, very large n consecutive integers. And then it says that prove that there are n distinct primes so that each prime divides each number, P1 divides m plus 1, P2 divides m plus 1. Okay, so in this problem there's just one main idea which solves it. We'll have a look at that. So basically first thing I do is I write m plus j as mj, just to shorten it. And then okay, so I'll need this statement. There can be at most n minus 1 primes or less than n. I mean, yeah, okay, it's a very quite loose statement, this one, but for this problem it works. So the first thing that you do is you take the prime decomposition of this, and you assume that let p1 to pm, the primes p1 to pm are the ones which are less than n. Okay, and now what you do is you look at the maximal of okay, of course m will be equal to n minus 1. Yeah, from this statement here we get this. Okay, now what? Okay, so now from this prime powers, you take the maximal of that, p1 to alpha 1, pm to alpha n, and all those. Let pj to the power aj is the maximum of this prime powers of the decomposition of mj. What can you say about this number? Because basically there are two main observations. First is that this has to be greater than or equal to n. That's one. Why is that? That's because if it's less than n, then what happens? First of all these primes which are greater than n, they will be all the powers will be 0 here. So alpha m plus 1 and onwards will be 0. So you will have mj equals to this is the product of these m prime powers, and since each of this is less than n, so all these prime powers are less than n, and then what we have, and since there are m of those, so this product will be less than n to the power m, and m is less than or equal to n minus 1, so this is less than or equal to n minus 1, and this is then less than m. So mj will be less than m. This is a contradiction. Okay, so this has to be greater than or equal to n. And now there is one more observation. If this is greater than or equal to n, it will not divide any other mj. Okay, and why is that? That's because it divides mj, and the difference of this, the distance of mi from mj, will be less than mi minus mj is I minus j, and this is actually less than n. So this will be less than or equal to this pj to the power aj. So pj to the power aj cannot divide this mi. Okay, and what does that mean? That means the mapping of mj to the power pj to all these pj to the aj, this is 1 1. Okay, so each mj is assigned a distinct pj to aj, and from that pj to aj you can map it to the corresponding prime pj, and that gives you all this and the assignment that you're looking for. So okay, alright, so that's also it. This is problem 5. It's geometry. It's slightly lengthy, but yeah, quite nothing difficult. It says let AB be a diameter of circle gamma and C be a point on gamma different from A. So yeah, like this we just need half a circle. Just to save space, I draw half of it. Take C on it, and let D be the foot perpendicular from C to AB. So this is D. Let K be a point on the segment CD such that AC equal to the semi-perimeter of ADK. So this AC is the semi-perimeter of this triangle ADK. It says show that the circle of ADK, so the circle which touches three sides, this side extended, this one CD, this DB, is tangent to gamma. So it also touches this point on the circle. So that's what you have to show. And how do we do it? So let's look at the two circles. So let's say one of them let's say this is the line CD, this DB, and let's say one of them is the circle which touches these two lines and the third line, and the next one is the circle which touches these two lines and this circle here. So what can you say about these two circles? So first of all, the center will lie on a straight line, which is the angle bisector 45 degrees here, and the distance of the circle from these lines will be equal to the radius. So if this is R, this will be RA here. Yeah. Okay. And now what does means if I show that if the radius becomes equal, if RA, if I tend it to R, then the centers will also coincide. And that basically means that if the radius of these circle become equal, that the circles will also coincide. Okay, so if R is RA, then the two circles will become the same. So that is what we'll show. We'll show the X circle, the circle which touches, this side, this one, and this one. The X circle and the circle which touches these two lines and the circle, they have same radius. And that will imply that those two circles are the same. Okay, so let's first of all, I choose the coordinate. Let's say this is as a unit circle, the bigger one. I scale it to 1. The center will be at the origin. This point A will have coordinates -1, 0. B will have coordinates 1, 0. C is a general point on it, so the coordinate will be cos theta, sin theta. If I drop a perpendicular on it, the y component will become 0. So D will have a coordinate cos theta and 0. Okay, so now let's look at the circle which touches A, B, C, D and the bigger circle. Okay, let's have a look at that. So again, this is the center here, 0, 0. And what I do is basically I join this line here and draw a perpendicular. Now what can you say about this line? So this distance is R here, so this is R. So this length, this is cos theta here, so this length will be cos theta. So this length will be cos theta plus R, since this is again the perpendicular from it. This will be R, and this will be 1 minus R. Why is that? That's because from this point, if you draw a normal to one of the circles, it will also be a normal to the other circle. Okay, so since it's a normal to both the circles, it will pass through the center of both the circles. So basically that means this point here, which touches the touching point of these two circles and the centers, that collinear, and this distance will be R, and since the whole radius is 1, so the remaining radius is 1 minus R. Okay, so here we can apply our Pythagoras theorem. That's what we get, and basically I solve for R. We have 1 plus cos theta, and at some point I convert it to half angles, and it's a little bit more simple. And then we get a quadratic, and we'll have two roots, and one of them is negative. We'll have a minus sign here. We omit that. We take the positive root. Okay, so we get this, and here you'll have cos square theta common, and you'll have cos square theta by 2 plus sin square theta by 2. That will be 1. So we have this. So R we can find it's 2 cos theta by 2 into 1 minus cos theta by 2. We'll show that the X circle will also have the same radius. Okay, so that's our part 2. So the X circle, we know the formula. It's delta by S minus S. So delta will be the area of this circle AKD. So we have to find this, and H is basically the height. So since we are looking at the X circle here, so we have to know this side. The first result that we have is AC is given. It's the semi-perimeter of this. So AC equals what? It's, the coordinates, so it's cos theta plus 1 whole square plus sin square theta square root. So that's 2 cos theta by 2. So S equals this, and we also have this length. AD is 1 plus cos theta. So this is S. AD is 1 plus cos theta. That's 2 cos square theta by 2. So that is S square by 2. So this length is S square by 2. Take this to H. Let's take this L. So one relation that we have is this plus this plus this is 2S. Okay, so from there we get L plus okay, and this is the second relation from Pythagoras theorem. L square minus S square is the square of this. So from this you get 12 plus 2h is this, and from this one you factorize, you get 2l minus 2h is to the 4 by this 12 plus 2h. This value you put it here, you get that, and you have 12 plus 2h and you have 12 minus 2h, and you basically subtract it, you get 4h is this. Okay, so we will calculate h, then we'll calculate delta, and then we get the x radius. So we have all this. So r is what we found in part 1, so this is what we just found, and delta is 1/4 h square. Okay, so it's base into altitude into half, so 1/4 h square. So now this was the calculation here. We had this, and basically simplify it, and at this point it's better to look at 2 by h. I will see why it inverted. Just subtract 2 by s. So now you can see you get hs in the denominator, which is almost the area, and you get s minus h the numerator. So that will give this, and here you multiply with I square, and now you have that h, you invert it to h square by 4, and s minus h, you'll have a factor of 2 here, so that's this, and this is the delta, this is that s minus h, this is the x radius, so this is r, and what is this equal to? S is equal to 2 cos theta by 2, substitute it here, this 2 will go away, this 2 will come out, so this is this, and this is r, so we have r equal to ra, and that also means that since the radius are equal, and then that implies those two circles are also the same. Okay, so that's what we have to prove. And this is problem 6, and this will not discuss because this problem is incorrect, and it's actually not impossible to find a counterexample if you work a bit. Again, this is from the website. Basically they've admitted that they've messed it up, so we'll not discuss it, I'll just stop here. So that was INMO 2019. If you want to write to me, you can email me, or yeah, so I'll stop here, and in all case, I hope you enjoyed the video, and I'll see you next time. Bye.